Alrighty, today we're talking about banked curves. Banked curves are very similar because we are on inclined planes, right? Can you see the car? Inclined planes. But we're going to be driving forward fast enough to where we're almost like driving into the slope and we're going to get a little bit of extra normal force out. And so typically on an inclined plane, what two main forces affected us? We have definitely gravity. And because we're on a slope or because we're on a surface, what else do we have? Because we're on a slope, what else do we have? Force normal. And back in the day, we drew this normal force just long enough to where our resultant, our leftovers, if I were to redraw this normal force down here, would bring us along the surface of the ramp. And so these red lines, they're not real. Maybe I should make them both dashed. They're not real lines. But that we would be just enough down the normal force would be just enough to push us down the face of the ramp. Our resultant is down the face of the ramp. How we accelerate is this leftovers of down plus this normal diagonal force. Okay? That's how it used to be, right? From there, we could see that our triangle is this right triangle, that this would be the angle of the ramp, and we used to say that the normal force would be equal to mg what? Cosine theta, and that our leftovers, our net force down the face of the ramp, would be equal to mg sine theta. And that's the way we would move, right? Typically, is down the face of the ramp. And that's all that was happening. Now, we're driving, and we're pushing this car forward around the circle. Do we want this car to go up or down the height of the ramp? No. We don't want the car to go up and down the height of the ramp. But we start off with the same two real forces. What are those two real forces? So, mg is still the same length. I tried to draw it the same length as over here. But my force normal, because I'm driving around in a circle, I'm allowed to drive fast enough to give me a little bit more normal force. Right? Our force normal. Because when we break this one down, and this one's easy to break down, when I draw the component upwards, we don't want it to go up or down the face of the ramp. And so what is this equal to? mg. And then side to side is my leftovers. And so the way we end up moving is also how I start spinning in a circle, the centripetal force. So let me move this force normal so that way it's not in our way. That in green over here we have our force normal. But this top leftover part is actually the force centripetal, or how we're moving in the x direction, how we're accelerating in the x direction. What do we need to know about force normal then? Force normal, cosine theta equals mg, right? The length of this side is force normal cosine theta. Yeah. So our force in the x direction, which is force centripetal, is equal to F in sine theta, and F in cosine theta equals mg. A lot of times, though, we don't see it that way. What we're going to be looking for is force normal. Well, let's just rearrange that. Force normal equals mg over cosine theta. You see how it's changed? This is our end result.
So fx would be...
And also, this is our what we need out of this conversation.
So we could rewrite that figure 1 as mg sine theta.
Yeah. Yeah.
Mg slope.
That's, I think so, but also we're going to need to be able to not only just have these memorized, but we're going to need to be able to show it and prove it every single time it's asked for it on the AP. And so we're going to practice this a lot, okay? So let's work on a sample problem. Let's get ahead and get started on a sample problem. So we've got the highway curves to the left with a curvature of 43 meters. R is equal to 43. The highway surface is banked at a theta of 22 degrees so that the car can take this at higher speeds. We've got a mass of 1, 2, 3, 4. And if we don't have, what is the normal force acting on the car? Wait. We know that we're going to have to derive our equation. So again, with the picture, let's just draw it on the car over here. We've got gravity. And I'm going to draw my normal force. Is that normal force going to be longer, shorter, same length as gravity?
Longer than gravity.
The height of it is going to be the same, so it needs to be longer. Right?
Yeah.
The height of it needs to be the same, so it should be longer. Okay. The height of it, so we're saying mg, we need to say that the force in the y direction equals 0, equals, not ma, it's 0, so it's not how it moves. I mean, it is how it moves. It's not moving up nor down, but
Equals mg minus fn cosine theta.
mg minus fn cosine theta.
Because it's moving in gravity's direction.
And so that's all that helps us say that force normal cosine theta equals mg. And that allows us to finally get to where we need to be. Force normal equals mg over cosine theta. Do we have those parts? Do we have m?
Yes.
1, 2, 3, 4.
So we have the theta.
Do we have g? Y'all know what g is. 9.8. And we have the theta, so over cosine theta, 22 degrees. Let me clean that up for those of y'all following along. So y'all plugged in chugging, you got what? 13,000? 13,040? Right. 13,040 newtons is our normal force. Is the normal force bigger or smaller than gravity itself?
Normal force is bigger than gravity itself.
Right. So the ground is actually pushing back bigger than gravity because we're literally using the curve of the road and the direction that we're going to drive into the road, because the curve of the road isn't just that it is banked, but also that it is curved, right? So we're actually driving into the road in front of us, okay? So we're getting more pressure against the surface than gravity itself on the banked curve.
Is that why we can drive faster on big curves?
And that's what holds us up, yes. All right, how fast can the car take the curve without skidding to the outside of the curve if there's no friction between the tires and the road? So what's the critical velocity? Is this we already solved out the up and down issues, right? So we need to worry about the side to side. So the net force in the x direction happens to be the centripetal force and also happens to be force normal sine theta. And I know we know what force normal is. We could just plug that in. But wait, is that all that is? But let's take a step back to right here and plug this in for funsies right there, because we need to see a couple of math things. FC. What is MAC? What's AC break down into to find the speed? Yeah, V squared over R, the tangential velocity. And then we said that this breaks down into mg over cosine theta. times sine theta? No, times sine theta. Alrighty. What is your math skills? What's your teachers tell you to do?
Take out common variable.
Take out common variables, so mass goes away.
So v squared over r equals.
What else is common? I've got,
There's a g in that v, isn't there?
there's 2 thetas. What's sine over cosine?
Y over x.
Okay, so to find the speed, I'm going to move over the r to the other side and take the square root. So I've got g r tangent theta rooted. I did a handful of algebra steps at once. Okay, this isn't showing our work in math class appropriately, but for us, this is what the bare minimum is. That we have rearranged it algebraically.
Wait. Oh,
Double check.
I thought there was a plus.
So 9.8, r is 43, tan 22 degrees. And we get the speed. What'd you get as your speed? All right, it is a huge radius. So do we need to be moving that fast? 13.05 meters per second. That is actually not that fast. That's slightly faster than you can run, but we're talking about a car probably. Right. I could probably run half of that. Alrighty, let's talk about this one. Part C. How would the maximum speed of Part B change if the friction was present between the tires of the car and the road? So for this one, I would draw myself a diagram and then explain what's going on. We know that we have how many real forces now?
Friction and gravity.
So we have gravity, normal, which is longer now. And we also have the availability of the force of friction. And when we start to add all of our forces together, our sideways force, or my FC, is now made up of what 2 parts?
Force friction and sine theta back end.
Force normal sine theta, just like before.
Mr. Kwan, I was wondering why would friction be going down?
Oh, good question. We could choose which direction friction's going, right? And so what I had said is we know that we're trying to maximize our speed. What happens if we go too fast? We would go up or down the face of the ramp. Up the face of the ramp, therefore friction will hold us back from up the ramp. Okay? So that's why I put friction down. You're right. We could choose either direction. But the maximum speed before we like slide up the ramp is going to be that. So plus, and this one's an interesting one because it is the x component of friction, right? This is diagonal, but we're worried about how it will go side to side, completely side to side. And so we could actually, even though it's typically mu force normal, there's a cosine. We're going to multiply and divide. I think we're going to multiply and divide by that cosine. So I think that actually disappears, interestingly enough. Anyways, this one I would write out in words. The maximum speed would increase because the component of friction in the x direction will add to our Fn sine theta, right? So the force normal's side-to-side component as well to create a bigger centripetal force. Does force friction have mass in it? mu mg
Yeah, technically.
cosine theta, or over cosine theta in this case, right? Because it's mu force normal, and force normal is mg over cosine theta right now. Right? Mu force normal, but our force normal is at an angle. But then our friction's at an angle too, and so we actually undo that cosine theta.
I'm trying to take out all the masses.
Wait, so the cosines are just.
Cancel, I think.
Yeah.
I think.
So it's just mu mg.
It's just mu mg at the end, yeah. All right. If we're traveling around a banked curve with the radius, oh, mega huge, 1,000 meters. This is like a whole racetrack, 4-kilometer wide racetrack or something like that. The truck has a mass of 2,000 kilograms. Maybe it's going like around a mountain or something. Who knows? Or around a valley.
It's a very circular code.
All right, so we've got 1,000 meters. We've got 2,000 kilograms. At what angle should the curve be banked to the horizontal so that the truck can take the turn safely? Exactly at 27 meters per second. So we've got a velocity, mass, and radius if no friction is present. So we want no friction either. Okay. So we need some sort of banked angle. If we're on this banked angle, what two real forces are we worried about? Force, gravity, and force normal. I'm going to draw that extra long so that way when I split it up, the height of it equals gravity, and the side to side is my centripetal acceleration. Force equals force gravity. That's force normal cosine theta equals mg. All right, so my up and down. That's the first place where that I would start. My net force in the y direction is equal to. Do we want it to slide up and down the face of the ramp?
Oh, 0.
No, so this is 0. MA is 0. And then what two things go up and down? mg and Fn cosine theta. And we're now able to say mathematically that they're the same. And now we have solved for force normal equals mg over cosine theta. If it feels repetitive, it's just to make sure that we know we're coming from the correct source material, that we end up with an equation that is opposite of us sliding up and down the ramp where it was mg cosine theta. Now it's mg over cosine theta. What happens in my x direction? The net force in the x direction is my force centripetal and also is my
Or it's 27 meters.
MA. That's MAC. Is also my... Well, let's just start with this. We have force normal sine theta equaling m v squared over r. We know what force normal is. Mg over cosine theta. And then we're going to multiply that times sine theta. Oh, yeah, that's good. Equals mv squared over r. Our m's cancel out, and then we get tan theta. So g tan theta equals v squared over r. Good. And then we need to find the angle, so let's move over the g. Divide out the g. So we have tan theta equals v squared over g. How do I undo tan theta?
Tan inverse of.
Yep. Inverse tangent of, or arctan of v squared over g. Is that it? Do we have the v?
Yeah.
27. Do we have g? 9.8. Do we have R?
Yeah.
1,000 meters. What doesn't matter? The mass has been canceling out. Okay. When we get to conic pendulums tomorrow,